Hello everyone, my name is Mohammad Pur Humayun. I hope you are all healthy and safe. In this video, we will continue the important and interesting topic of artificial neural network, one of the most important topics, methods and algorithms in data science, machine learning and AI. Last time we had a brief introduction to artificial neural networks, also known as neural networks. We mentioned that it's a group of machine learning systems and models inspired by the structure and functionality of biological brain, specifically the human nervous system, or particularly the brain. Artificial neural network can learn from data and generate models that get a number of inputs, exactly like our brain. It gets inputs, in this case the features, and generates some outputs or commands, as we have for our brain. So we mentioned that the first step to mimic the brain or to simulate a biological neural network is to simulate a neuron first, which is the smallest unit of our nervous system, the smallest unit of our brain, or it's in fact the nervous cell that we call it neuron. A biological neuron looks like this. It has some inputs, some outputs, and a body cell. And we mentioned that this is a very good model to simulate a biological neuron in a computer. So it has some inputs, x1, x2, x3, and so on. We multiply each input by a weight, and then a linear combination of them, and then a non-linear function, which is called activation function. And then it generates the output. We talked about some of the activation function. It should be non-linear. And we mentioned that by connecting some of these neurons to each other, we can build a neural network. So as I mentioned, the neural networks is in the form of layers, the structures in the form of layers. The first layer is called input layer. The last layer is called output layer, and the middle layers are called hidden layers. Okay, you may have as many as layers as you want, but later I'm going to talk about the complexity of a neural network and the problems that we have, such as overfitting and so on, and how to resolve them. All right. So now, before we continue, I need to define some notations that we will later use to define a network and then later to train the neural network. So first of all, this is a standard notation that we use for neural networks, and you can see this in most of the textbook and articles to define different parts and different parameters of a neural network. So first of all, we show the activation functions, or in fact a neuron, with a subscript I superscript L, which defines the output of the activation function of unit I in the hidden layer L. Okay, so this guy is unit 1 in the hidden layer 1. This is unit 2 in the hidden layer 1. This is unit 3 in the hidden layer 1. And this one is unit 1 in hidden layer 2. We could have another, for example, neuron here, something like that. And if we had it, then it would be A22. Okay. We can have another layer. Okay, we could have another layer, for example, and then same thing. this guy would be 1A3. Okay, so remember, the subscript indicate the neuron or the unit number, and the superscript indicates the layer. And then we have weights. Okay, so Wij superscript L is the weight of the path from unit J in layer L-1 to the unit I in layer L. So in fact, this weight shows this Wij shows the weight of the path from unit J to unit I of layer L. So look at this. So again, these are standard definitions that we have to use to define different parts of the network. So this guy is W21 superscript 1. It means that it goes from the first input to the second node or second neuron of the first layer. So this is layer 1. Okay, and similarly, this guy right here, it represents the weight going from second neuron of layer 1 to the first neuron of layer 2. Okay, so these are the notation that we use. And as I mentioned last time, the whole process of training means that we have to find these weights. Okay, so these weights will define our network, how it's connected, what's the structure. So it turns out that some of them can be 0, for example. If it is 0, it means that this wire is disconnected. Okay, so remember that. So the process of training means learning these weights from data, and I'm going to show you how we can do that later. W superscript L, as you see, it's capital W. It means that it represents a matrix. Is the matrix of all weights from layer L-1 to layer L. Okay, so all of these weights you can put, for example, all of the weights here. We can put all of them in a matrix. Okay, all of those weights that goes from this layer to this layer, all of them, and we call it like capital L. All right, and as I mentioned last time, we have bias in each layer. Usually in a neural network like this, we don't show them because we don't want to make the network too complex, but in all of our calculation, it is there. So for example, there is a bias right here and there is a bias right here. So for example, I call it B0, and it goes to all of these neurons, and there is a weight for each one of these paths. And here for this layer, again, we have another bias, for example B1, okay, that goes to this guy, and it has a weight too. So this is the bias, but sometimes we don't show it in our network because we don't want to make it too complex. But remember, there is a bias for each layer, which is a constant value added to all of those inputs. All right, so given these notations, let me show you, for example, if you want to calculate this guy, the output of this network, what it looks like. So what is A11? Okay, so of course, as you remember, this activation function looks like this. So it has, of course, a first of all, activation function that applies on the output of this linear combination. So it can be in the form of g of or f of, this is your nonlinear function. Okay, from here we have b1 multiplied by w101 plus x1 multiplied by w111 plus x2 multiplied by w121 plus x3 multiplied by w131. Okay, and then g of the whole thing. So this will be the output of the value, this value here, right here, a11, and this output will be the input of the next layer, and so on. And the same thing for the other network neurons. So here you go. This is a1. This is the nonlinear function that we have here. Okay, and here you go. This is the function only for this guy, the output of this point right here. This is a11, and we have the same thing, a21 here and a31 here, and these are the inputs of this one. So we usually hide the bias term to make the picture, the structure simpler, but we should take it into account. So remember that we have it anyway. So if we do the same thing for all of these three neurons, we will have a structure like that at this layer, the output of this one and this one and this one. It will be like that. And then y, so the output of this first layer will be the input of the second layer. So same thing for y, right? So y, which is also equal to a12 right here, is the same thing, g of, so we have bias here. Again, it's hidden, but it is there. It's available. So this weight multiplied by the value of this guy. Here you go. And then this weight multiplied by the value of this one. And then this weight multiplied by the value of this cell. Okay, and everything then passes through that non-linear function g, which is inside this. Okay, and then it creates a y for you. So these four equations right here tells us how you create y from these x inputs. Okay, only using these four equations you can define how you can create y out of these x inputs. So as you see, it looks like a very complicated, a lot of processing calculations. And remember that this network is very, very simple. This is maybe the simplest network. It only includes 4 neurons. Okay, remember, in our brain, again, there are about 100 billion neurons. So look at this number. So this, only using 4 neurons, we have to do these calculations. And if you notice, as we move forward, if we add more hidden layers and more hidden layers, the network will be more complex and more complex. Remember that so these are the inputs, okay, and y is the output. The unknown part of the equation is w. Okay, so these are the unknown part of the system, and we have to learn these unknowns. We have to find these unknowns from data. So in this case, we have 4 times 1, 2, 3, 4, 16 unknowns, right? We have 16 unknowns here in this equation. in this very simple neural network that has only 4 neurons, we have 16 unknown values that we have to find them in the process of training. So in the process of training, suppose that you provide 3 features, for example, humidity, temperature, and wind speed to our system, and you want it to predict if tomorrow is rainy or sunny. Okay, that's simple. You provide the data in a training process, and in the training process the algorithm will find all of these weights for you, so that this neural network can predict if tomorrow is rainy or sunny based on these features. Okay, you can apply it for many different applications, and I will show you some of them, but this is how it works. All right, so as you see, this group of equations are a little messy, especially if you add more neurons, and variables will be added. If you add more layers, for example 3, 4, 5 hidden layers, this system will be very complex. So that's why we use a vectorized version of all of those things, which makes it a very compact and neat type of visualization. Vectorized implementation of forward propagation. So by the way, this is called forward propagation because we move forward in our network. Okay, we propagate the inputs by moving forward into the network. So this is what we had, all right, for the output of these 3. Okay, let's define a vector. Let's put all of these 3 values in an array, in a vertical vector, something like that. Okay, and then put all of those weights. So this is the matrix of weights that I talked about. All of these weights, all of these, for this layer alone we have 3 times 4. So we have, remember, there is another bias here. Okay, so we have 4 inputs here and we have 3 here, so we will have 12. 4 times 3, 12 weights for this layer alone. Okay, so I put all of those 12 weights here in this matrix, and this is weight matrix, and then I put all of these inputs into another vector or array. I call it X input vector, and as you see, this is bold, it means that it represents a vector. This is bold, it means that it represents a vector. So if I do this, then the equation, everything will be so simple. It will be this, that's it. So the equation will be very simple. G, of course, the nonlinear function of this matrix multiplied by this vector, it gives me this vector. Okay, that's simple. So let me show you why. So here you go. The first row, okay, multiplied by this column will give me this element. Why? Because look at this, if I multiply this, the first element of this will be multiplied to this one, the second element multiplied by this one, and this third one multiplied by this one, and the last one multiplied by this one. It makes this equation for me. Okay, and then g of that, which is a nonlinear function, it gives me the output, which is this guy, which is the first element of that. Okay, similarly for the next row. So the first row, the second row multiplied by this column gives me the second element, and here is the equation. And similarly for the third one, the third row element-wise multiplication to this guy will give me the third element of this. Okay, so all of those complex equation will be represented only in this simple equation. Okay, so this equation includes everything. Very simple. All right, but we have to define these vectors. Okay, so now after having this, the system will be very easy. Okay, so you can add as many as neurons you want, like 10 of them, 20 of them, 100, thousands of them. Okay, because remember, we want to make a very complex neural network. We want to mimic our brain to perform very complex tasks. Okay, and this is how it works. We need to have a compact form of equation that we can include any type of neurons or any type of inputs in that by defining these matrices, and the equation is still cover all of those equations. So this is what we do. And another thing is that we can add as many as layers we want now, so there is no limit. So the only thing is that for next layer, this guy will be the input, okay, and y will be output. So y will be another w2 times this, and g of that. Okay, so this is how you create y. Here you go. Okay, so y, which is the output of your network in this case, which is in fact equal to a12, the output of this neuron, is equal to this. So same thing, this guy multiplied by this guy multiplied by this guy multiplied by this, and then g of them. It creates y, and you can use vectorized representation to show it. G of w2 will be this guy, these weights, times a1. Look at this. This is bold. It means that this is the vector of these a's. So this guy multiplied to this, or this one. This is a row. So w2 looks like this: 1 1 1 2 1 3. If you multiply that to this guy, it gives us the output. Okay, very simple. So now we don't care how many layers we have, we don't care how many neurons we have. Of course, the computational complexity will be higher, but generally speaking, the equation will be the same. So this simple equation represents everything for each layer. So this is for layer 1, this is for layer 2, and so on. So don't forget the bias. Okay, we always have a bias here. So again, we will have a bias right here, b0 for this layer. We have another bias here, and so on. Okay, we should always remember to include a bias. All right, this is the notation. So this was the notation that we need to know, because later we want to train our neural networks on data. And again, as I mentioned, the process of training is just to find these weights. Okay, so when you find these weights, it is like training the brain. It is like the brain of a newborn baby, for example, that tries different things, and based on the experience, based on the information that it collects from the environment, it learns. Okay, so at the very beginning, a newborn baby, for example, he or she gets hungry, he starts crying. Okay, and when he cries, he receives milk, for example, and then its brain learns that every time you are hungry you can cry and you receive milk. Okay, so this is exactly the same situation. So you have a neural network. At the very beginning the neural network is completely raw. We can start with random weights, but by time when you provide more data and more data to the system in a training process, this small brain starts learning. It starts learning from experience, it starts learning from data. All right, a network can have more than one hidden layer. Okay, of course the model will be more complex. So this will be the first hidden layer. And then second hidden layer. The network will be more complex, but those equations that I extracted works. Still, all of those equations work. Doesn't matter how many layers you have. You just add more equations, and it was very compact equation, so it was easy. Another thing to remember is that your neural network can have different outputs, okay? Not only one. So far, all of the classifiers that we learned in, for example, last time in our previous classes, you had one output that could predict, for example, a binary classifier, or for example, in iris flower, we had three labels. Setosa, versicolor, virginica, we had three values, so it was multiple labels, or cloudy, sunny, rainy, multiple labels, but still it had one output. Okay, only one output that had different values. Here in neural network you can have multiple outputs, okay, to predict different things simultaneously, or predict one single thing using one hot encoding. This is very important. This is very useful. You can predict completely different things at the same time. For example, detecting an object and detecting the location of the object and size of the object in a picture. So in one picture, okay, so there is, for example, I don't know, a tree right here, okay, a tree right here, and the algorithm can detect that if this is a tree or not, and then the location of the tree, and then the size of the tree, the width of that, the height of that, all together as different outputs of your network. Okay, so this is amazing. This is very helpful. That's why it's so popular in processing images. Or I can use one hot encoding. It's a very common thing. So suppose that I want a classifier that detects 4 objects in a picture. Okay, cat, dog, horse, and bird in one picture. And then I can use this structure. Okay, it is like one hot encoding for the output. I use when I have a cat, I generate 1 0 0 0. Okay, when I have a dog, I generate 0 1 0 0. When I have a horse, it generates 0 0 1 0, and so on. Okay, and then when you train, listen carefully, when you train your neural network using this, I will talk about this structure and all of these things in deep learning when I cover deep learning part. But as a quick note, when you train your neural network and gives for example, pixels of this image as inputs to your neural network, but when you provide pixels of this to your neural network and train these neural networks to detect this object for us, it gives you, if it gives you 0 1 0 0 0, it means that the algorithm with 100% certainty it predicts that the object is cat. Okay, but if it generates something like that, for example, so this is a common thing that happens in real life. So you see something like that, 0.6 here and 0.4 here and 0 here, 0 here. It means that your neural network predicted that this object is a cat with the probability of 60% or dog with the probability of 40%. Okay? So this is how it works. So it can give us the certainty, the probability of that this object is a cat or dog or whatever. Okay? So this is another advantage of having several outputs in your neural network or in your classifier. It gives us the certainty of detection. And this is very, very important and useful, and we will talk more about it later. And so your data will look like that. So before, as you remember, only the features were a vector and the output was a scalar before this. But now your output can be a vector too. Okay, because it gives us the probability of each object, for example, chance of this object being each one of those items or classes. All right, so deep neural network or artificial neural networks generally is a great algorithm to process complex data such as images, okay, such as video, such as audio. So this type of data, like image or video, they are very complex data because, first of all, it's very high dimensional data, because each one of these pixels, each pixel of an image can be a feature for your machine learning model. So you will have a lot of features, and the pattern of them, the pattern of detecting the face of a cat and compare it to a dog, because the pattern that is available, for example, the sharp ears compared to these round ears and so on. So these are patterns that are available in the data, and our brain detects it and learns it by time. So a kid, for example, a 2-3 years old kid, you show him a cat and tells him this is a cat, and 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 that is a dog, and that's a dog, and that's a dog. So the brain of a baby will learn by time, by seeing different patterns, by seeing different examples of cats and dogs. The brain of a baby learns over time, and it can discover and extract the pattern of a cat and dog by time. So after that, when that baby sees a new cat, okay, or a new dog, its brain can detect if this is a cat or a dog and makes this prediction. Okay, so it discovers the pattern, learns the pattern, and makes prediction in future for future cat, although it is the first time he sees that. So our neural network that we train will do the same thing. So we train our neural network to do exactly the same thing, to see different patterns and learn from this and discover the pattern in the data, in the training data, and then learn, for example, the difference, learn the pattern of a cat, learns the pattern of a dog, and learns how to distinguish between them, the differences. Okay, and then when it sees a new cat, it can detect if this is cat or dog. These patterns are very complex in images and videos, and to process complex patterns, we usually need a complex machine learning model like artificial neural network. That is why artificial neural networks are the best approach for processing, for example, images or videos or audio. But still, the most sophisticated and the most complex neural networks that we have built so far, they are is still very simple compared to our brain. Although our recent neural networks are very capable, they can detect an object with the accuracy of close to 100% in many cases. So the detection is really good for recent neural networks. They are very well trained networks with millions of images. But still, remember, our brain includes 100 billion neurons, and we have trained it over many years, right? If you're 20 years old or you're 30 years old, it means that you have trained your brain over 20 years. So, although neural networks is the best approach to detect objects, but they are still very complex problems in real life that sometimes it's easy for our brain to detect if this is a dog or muffin, but although it looks easy for our brain, this is still a challenging problem for computers. And remember, neural networks is something that many scientists all around the world are working on that to improve the accuracy, train and train and train with many challenging data sets. And as we move forward, every day we see the improvement in the accuracy of artificial neural networks. So in next videos, I will continue by talking about training neural networks, how we can train neural networks, and later we will have practical tutorials in Python using different approaches. I will talk about scikit-learn, and then I will talk about TensorFlow, and then Keras, how to build and train a neural network in TensorFlow and Keras. Thank you.